Hello, today we're going to solve an interesting integral relating to the log function, and we're going to use a nice technique which we've seen before. We're going to use Taylor series, so maybe use that as a hint and see if you can solve this integral quickly, and otherwise just enjoy the solution here. So as I said, we can use Taylor series here. Maybe we'll start with the most basic Taylor series, which is also basically a geometric series for 1 over 1 minus x, which is going to be equal to the sum from n equals 0 up to infinity of x to the power of n. So this is a fairly well-known Taylor series, and we're going to use it, and we're going to take the antiderivative of both sides, which is going to give us the negative log of 1 minus x, and that's going to be equal to the sum from n equals 0 up to infinity of x to the power of n plus 1 divided by n plus 1. So we take the antiderivative term per term on the right hand side there, and on the left hand side we just apply some kind of inverse chain rule. That's why we have the minus sign there. So notice if you were to take the derivative of the left hand side, you would get 1 over 1 minus x. So now maybe we'll take this minus sign and we'll pop it over to the other side just to get a nice expression for log of 1 minus x. But also notice that of course we don't have log of 1 minus x, so we kind of have to substitute x for minus x, and then we will get 1 minus minus x, which is obviously 1 plus x. So this means that log of 1 plus x is equal to minus the sum from n equals 0 up to infinity of minus x to the power of n plus 1 divided by n plus 1. Okay, nice. So maybe we'll use that immediately, and we're going to pop it in the integral. So we're going to get the integral from 0 to 1 of the sum from n equals 0 up to infinity of minus x to the power of n plus 1 divided by n plus 1 times 1 over x dx. Oh, and I forgot a minus sign. So maybe now notice that we could take this 1 over x and this minus sign and use it as 1 over minus x, and we could just scratch one of these minus x's in the sum. So we're going to do that. We're going to use this minus sign, this 1 over x, and we're going to get rid of that plus 1 in the power there. Okay, nice. And now at this point, we're going to do two things simultaneously. Namely, we're going to take the minus 1 and the x separately, and we're also going to switch the integral and the sum around. So we're going to get the sum from n equals 0 up to infinity of the integral from 0 to 1 of minus 1 to the power of n times x to the power of n divided by n plus 1 dx. And of course we can take everything which is not involving x out of the integral as a constant. So we're going to get the sum from n equals 0 up to infinity of minus 1 to the power of n divided by n plus 1 times the integral from 0 to 1 of x to the power of n dx. Now of course notice that this integral actually is really simple because it's just a standard integral we all know from like calculus classes. So we're going to have the sum from n equals 0 up to infinity of minus 1 to the power of n divided by n plus 1 times x to the power of n plus 1 divided by n plus 1 evaluated from 0 up to 1. So we're going to get the sum from n equals 0 up to infinity of minus 1 to the power of n divided by n plus 1, and then times, let's see, 1 to the power of n plus 1 is just 1 divided by n plus 1, minus, of course, 0, so we're not going to write that, and so eventually we just have this sum with n plus 1 squared. So now we've got this sum, and let's first maybe get rid of this n plus 1, which is kind of annoying. So we just have the sum from n equals 1 up to infinity of minus 1 to the power of n plus 1 divided by n squared. So I just changed the parity on this minus 1 to the power of n. Okay, and now what I'm going to do is I'm going to apply a little trick to convert this into something we actually know. So I'm going to do minus the sum from n equals 1 up to infinity of 1 over n squared. Now I can't just do that, so I also have to add the same sum in. Okay, what is this? This doesn't look logical at all. Why did we do this? Now, I'll show you immediately. First, I'm going to write a couple of terms out, right? So for this part here, we would get that all of the odd cases of n give us positive numbers, and all of the even cases of n give us negative numbers, right? So we would have something like 1 minus 1 over 4 plus 1 over 9 minus 1 over 16 plus dot dot dot, right? And then we have this second part where everything is just positive, but we do subtract it, right? So we get 1 plus of course this sum from n equals 1 up to infinity of 1 over n squared. So I just quickly wrote it like that. We could have just analyzed the sums as well, but this way a nice extra step to make sure everyone knows what's going on here. So basically all of the odd terms for n are going to cancel out, right? So if we look here, we have 1 minus 1, 1 over 9 minus 1 over 9, and so on and so forth. But we also have the even terms twice now, and negative, of course. So here it's negative, then we have the negative ones again, and so on and so forth. So in the end, what we get is all of the odd terms are going to cancel out, odd terms for n. We have minus 2 times 1 over 4 plus 1 over 16 plus 1 over 36 plus 1 over 64, and so on and so forth. Plus, of course, our sum from n equals 1 up to infinity of 1 over n squared. Now, this left part is, of course, all of the even terms of our sum, which means it's going to be equal to the sum from n equals 1 up to infinity of 1 over 2n squared, and we still add our sum. Another way to look at this part over here is that it's just this sum divided by 4, right? And we can see that here as well, because if we take 2n squared, we get 4 times n squared. So of course, writing that out, we have minus 1 over 2 times the sum from n equals 1 up to infinity of n squared plus the sum from n equals 1 to infinity of 1 over n squared, which of course gives us a half times that sum, which is the Basel problem actually, which I recently proved. And the Basel problem is this sum, which is equal to pi squared over 6. So in total we have pi squared over 12. So I'll link down below to the proof of this last fact over here. It's quite a nice proof, so I definitely recommend watching it if you're interested in solving these tougher integrals, because they often rely on at some point you realizing, oh wait, this is a well-known sum, which is in this case the Basel problem, pi squared over 6. So thank you so much for watching. We've got a very nice solution. Notice that we have this integral only using log functions, and we end up with this pi squared, right? So amazing. Thank you so much for watching. Till next time.